Hello everyone, my name is Joshua Liu. I'm very glad to present our work in collaboration with Professor Dan Nathan in Department of Computer Science and Learning Research and Development Center at the University of Pittsburgh. The Intention Adaptive Large Language Model Fine-Tuning for Text Derivation Generation. So here is background. Text derivations aim to generate derivation based on specific intentions, but the writer's intentions are difficult to implement due to their entangled multi-intent nature. For example, the same text is revised based on different intentions. On the left, the single intent derivation that changes the text in terms of the meaning. On the right, the multi-intent derivation aims to improve the text in terms of clarity and fluency. These are great examples to illustrate the challenges to generate successful derivations based on specific single intent or multi-intent derivations. The recently large language models have shown success in generation tasks, but there has been limited exploration in derivation generation, largely because large language models are fine-tuned on instruction-based rather than intention-based tasks. For example, in an instruction tooling problem on the right, it shows very implicit intentions like more appropriate. This instruction-based fine-tuning relies on contextualized understanding of the prompt, but it's unsure if the large language models really learn the intentions from the prompt and implement them in the generation. Therefore, we need to fine-tune large language models to align derivations with specific intentions like clarity or fluency. In other words, we need to learn the intentions before we generate derivations. So based on that, we're interested in 3 research questions. First, can large language models align intention prediction and derivation generation tasks through selected large language model layers? Second, can large language models generate effective derivations using even small corpora? Third, can large language models be generally efficient across different PFT adapters? To answer the research questions, we propose intention tooling, which includes 3 components. First, find important large language model layers to fine-tune because not all the layers are necessarily being used. Second, transfer intention representations learned in the first task, intention prediction task, to the second task, derivation generation task. Third, we can generate single intent and multi-intent derivations. So for the first step, we want to find important layers. Based on the prior work that developed algorithms to select important layers for intention prediction task, specifically, the prior work proposed the important layers and redundant layers for different distributions in terms of layer-wise gradient norms. So they transfer the distribution problem to a layer splitting problem, trying to find the optimal split that separated all the layers into important set and a redundant set, and use important layers to learn intention representation. So in the derivation generation task, we want to find the frequently used large language model layers in the intention prediction task for derivation generation because those layers are well learned on the intention information. We proposed the holistic frequency score, which measures how frequently a certain layer is used in the prior task, and use a layer splitting algorithm to split the layers into important and redundant sets. We want to transfer the layer-wise weights as well as their importance learned from one task to another task. We fine-tune the 2 tasks sequentially to minimize the GPU consumptions, but also based on the derivation theory that suggests derivations are driven by the writer's intentions. We propose a layer alignment ratio to measure the alignment between important layers in the 2 tasks. Specifically for the task-agnostic layers, the layer importance keeps it consistent across 2 tasks. In other words, the important layers between the 2 tasks are the same. The task-specific layers, their importance reverses across 2 tasks. In other words, the important layer in the first task will be redundant layer in the second task. So we use a layer alignment ratio to quantify the task-agnostic layers versus the layers used in the generation task. We implemented intention tooling with Mistral 7 billion Llama 3.18 billion and Quant 2.514 billion, compared to the small language models and the large language model. We visualize the large language model layer-wise alignment across the two tasks. The green box is from the intention prediction task. The brown box is from the revision generation task. So we observe the top and the bottom layers have more alignment than middle layers. And Llama 3.18 billion and Quant 2.514 billion have more alignment than Mistral 7 billion. So based on that, we argue large language model layer importance might be an intrinsic characteristic shaped by their architecture design and pre-training, because more than half of the layers aligned across large language models and corpora as shown in the table below. This consistently demonstrates the feasibility to align the two revision tasks through selected large language model layers. In terms of the performance, we show that single intent revisions outperform PFT and the classic baselines using the intention tooling, except for Mistral 7 billion, but best for the Llama 3.18 billion. Sometimes even better than full fine-tuning by using all the layers. So it suggests the layer alignment and the layer importance might influence the results, because the Mistral 7 billion usually have a low alignment. For the multi-intent revisions, we observed the Mistral 7 billion model performed better because the alignment ratio improved from 50% to 68%. Again, the Llama 3.8 billion and Quant 2.514 billion consistently outperformed baselines. So we argue that intention tooling works best with task-agnostic layers. We measure intention tooling efficiency by plotting its loss convergency during the fine-tuning. So the intention tooling has faster fine-tuning loss convergency across the three datasets regarding Llama 3.18 billion. So we evaluate the intention tooling with different adapters. The table on the left shows that intention tooling has largest GPU savings using DORA adapter compared to the standard PFT. And the table on the right suggests LoRa stands out for minimal GPUs and best performance on the iterator corpus. And the bottleneck achieved the highest performance on the archive revision corpus, but requires 10% more GPUs than the LoRa. So we show in quality analysis on this slide comparing human revisions versus large language model generated revisions. On the left, it shows that although there is no exact matches between human and large language model revisions, but large language models improve the revision in different way. On the right, it shows multi-intent scenarios, including clarity, coherence, and meaning change. So human has a lot of the revisions in the text, but large language models attempt to perform minimal revision in this scenario. So in conclusion, we can align intention prediction and revision generation tasks through selected large language model layers. We can use large language models to learn intentions and then generate successful revisions using small corpora. And the intention tooling is efficient across different PFT adapters. Our code is online. Feel free to scan the QR code if you're interested in reading our paper. Thank you.